All right, welcome everybody back to lecture number 2. So today we're going to talk about why nuclear physics on the lattice is so hard. There are lots of reasons, but this is the biggest. This is the so-called signal-to-noise issue, or the bane of every nuclear lattice person's existence. And this is why calculations involving nucleons are exponentially more difficult than calculations involving mesons. So first, we're going to just review correlation functions and their time dependence. I'm sure you all know this, but so we can at least get my notation down so you can understand what I'm talking about. So we put down some operator that has the quantum numbers that we're interested in. We create that state at, well, not that state. We write down a creation operator with those quantum numbers at time t equals 0, and then we annihilate it at some time t later. And we can insert the time evolution operator, e to the minus ht. And then insert a complete set of states. So the time evolution operator takes us from the operator at t to the operator at 0, so that now these are at the same time. Then we insert a complete set of energy eigenstates. And note that my brackets here, we are taking this with respect to the vacuum. And because of this Hamiltonian operator here, we get this sum of exponentials times some overlap factors, which tell us the overlap of our operator onto the nth energy eigenstate. And then if we're interested in picking off the ground state, we take t to be very large, and this guy, trying to figure out how much I can fit in here. I'm writing too big. Hang on. Okay. Okay, so this will just pick off the ground state because all of the higher energies will be exponentially suppressed compared to this term. Okay, so this is the signal that we're interested in. So in particular, oops, there we go. Nope, there we go. The signal that we want to look at, if, say, we wanted to look at a baryon, would be, in a very sketchy kind of way, our operator would correspond to 3 quarks, and each of these quarks would have to have whatever quantum numbers you're interested in, and they'd have to be tied up in such a way that you produce a baryon. But for this argument, it's sufficient to just say it corresponds roughly to a 3 quark operator. And now the operator that we have inside our correlation function, we know that the first thing we do is integrate out the fermions. And so once we've integrated them out, that means we've performed all the Wick contractions, but roughly what it gives us is 3 quark propagators. So that's what I mean by S sub q. And they propagate from t equals 0 to t equals t. Okay, so I'm going to use a kind of schematic way of showing that. So basically this is going to correspond to 3 quark propagators, and let's presume that this direction is positive time. So what I mean by this is that I am taking 3 quark propagators and averaging over the gauge field configurations. And so this guy at large times should fall off exponentially with the mass of whatever baryon I've created times time. Okay, so this is just kind of a shorthand way of denoting what this correlation function is doing. And so this is the signal we would like to see. All right, and now what we want to know is, so we know the time behavior of the signal. We know we have to do Monte Carlo to get this average over gauge field configurations. So there is going to be some statistical noise associated with this averaging process here, averaging over the gauge configurations. So the noise is defined to be sigma squared over n, where n is the number of gauge field configurations that we use. So in particular, we want to look at this sigma squared here, because that's what's going to tell us the time dependence of the noise. So sigma is related to the square of the operator, right? So we say that the variance of some operator goes like this. So it's the difference between squaring the operator and then averaging minus averaging and then squaring the operator. So this guy here, we already know, because this is just the signal squared. So this guy is going to go like e to the minus 2 m baryon times time, because we're squaring it. So the thing of interest is what is happening here. So to get that guy, we need to first square our operator and then perform the average. So if you'll recall, our operator was something like 3 quark propagators. So what is this? The square of that. So we need to know what S dagger is in order to look at the magnitude squared. So this guy, daggering it changes the time direction, so that instead of going from 0 to t, it goes from t to 0. And we take the complex conjugate. This guy corresponds to an antiquark. Okay, so now if we look at the magnitude of our operator squared, I realized that I'm being a little bit sloppy here. So because I used this O to correspond to just the annihilation operator. So let me fix that. So this was meant to be just for some generic operator. I'm at a loss for symbols. I'll just call it capital O and not curly O. Okay, so now we want to look at the magnitude squared of our operator, which hopefully you recall is O dagger O, curly O dagger, curly O. Okay, so the magnitude squared of that will correspond to, okay, I'm tripping myself up because I'm trying to write it as a magnitude. All right, let's just do it. So the magnitude squared of SQ from 0 to t cubed, which is what our operator was before. We want to magnitude squared that guy, so that will be S dagger, or let me write it as S star from t to 0 cubed times S from 0 to t cubed. Okay, so the thing that lives inside the variance for a baryon is equal to this. So now if we want to look at this in our, what happened? Yeah, where did we go? Okay. In our kind of pictorial way that we had, so we have 3 quarks propagating forward in time. And then we have 3 antiquarks that propagate backwards in time. Okay, so I wrote this in a suggestive way. I didn't write it as this guy. So this might be what you would picture after I wrote this. And so you might think that this will decay with e to the minus 2 m baryon T, because we have a baryon here and an antibaryon here, and they both have roughly the same masses. But I wrote it in this way for a reason, because as T goes to infinity, we're going to pick out the true ground state of the system. And that turns out not to be a baryon and an antibaryon. It turns out instead to look like 3 pions. Or, sorry, we're talking about a more general baryon. I didn't specify that we were talking about up and down quarks. So this would be like 3 mesons. Because we have 3 pairs of quarks and antiquarks. And hopefully you know that mesons are a lot lighter than the baryons in nature. And so this guy will be the true ground state for the variance. And again, this is just schematic. I didn't include the second term because we know how that one scales, and we know that it's going to scale with the heavy baryon mass. So we're just looking at the first term. And so yeah, we find that it falls off with this pion mass. And so let's see. So in nature, if we're looking at, say, the nucleon, this guy is about 935 MeV, and then the noise would correspond to 3 light quark-antiquark pairs. So that would be 3 pions, which are about 135 MeV. If we now look at the signal to noise ratio, so we said that the, hang on one sec. Okay, I just want to make sure I'm not skipping anything. Fine, okay. So we said that the signal that we want goes like e to the minus the mass of the baryon times time. We know that the noise, yes, the noise scales like the variance, and we already said that this first term is going to be much bigger than the second term because 3m pi is much smaller than 2mb. So we're only going to keep the first term. So it's going to go like e to the minus 3m pi t over n, and then we need to take the square root because we only want sigma, not sigma squared. So then this, therefore, goes like root n e to the minus mb, I wrote pi again. This is the meson for a generic case. So it goes like e to the minus the difference between the baryon mass and 3/2 the meson mass times time. And so if you plug in, for example, these numbers for the nucleon and the pion, you see that at the physical point, your signal will be very quickly getting swamped by your noise. And so in practice, what that means is that you'll need an exponentially large number of configurations in particular, you'll need e to the mb minus 3/2 mm t to number of configs to get a signal at time t. So this is a problem since we want the ground state. Obviously, we're going to want to go to very large t, but each time slice will be exponentially less precise than the previous one. And if we want to scale our error bars down lower, we'll need exponentially more configurations, which requires exponentially more computer time, which hopefully by now you all know is not a reality that we live in. Okay, and then finally, so you may have already seen this in looking at single nucleon matrix elements or something like that. However, this really becomes a problem when we start talking about nuclear physics, because you can repeat this argument that we did before and look at the noise for a nucleus, if we wanted to look at a multinucleon nucleus, where you had, say, A numbers of nucleons, and just ignoring interactions because interaction energies are all much smaller than these masses. You can see that this pretty easily generalizes to where if you have A nucleons, it's going to be A times this exponential factor here. So the number of configurations that you might need in order to get a signal for 2 nucleons is exponentially less than you would need to get a signal for 3 nucleons, and so on. And exponential behavior is not something any of us want to deal with. So we're going to have to come up with solutions for getting around this. All right, so I will end this video here, and we will resume after the question.